let me talk to you guys about experiment number 8. Okay? And give you some background information for that. We're talking about intermolecular force. And intermolecular forces are the forces between attractive forces between chemicals. If you have a chemical like nitrogen, dinitrogen, in which there's a triple bond between one nitrogen atom and another, then the bonds that holds one atom to the other is called an intramolecular force. But the force that holds one nitrogen molecule near another nitrogen molecule, that's called an intermolecular force. One force keeps the atoms together, the other force keeps the neighbors together. Okay? Intra is a pretty high type of force. These are in the order of about a couple of hundred kilojoules to a couple of thousand kilojoules. Just to break bonds, that's how much energy you have to invest. On the other hand, to separate chemicals from each other, to make one chemical go from a solid to a liquid, that goes from the order of about 0.05 kilojoules to about 40 kilojoules. You can see that these forces are much weaker than the bonds that hold atoms together. And so it will require less energy. But it's also the force responsible for the different phases of matter. Matter, as you know, has a solid, liquid, and gas phase. And it's the intermolecular forces that is responsible for these phases. When we have a solid phase, you actually have chemicals that are near together and are sticking next to each other through these intermolecular forces. You can think of them as glue that holds one molecule near another molecule, one atom near another atom. These are the glues that hold it. As soon as you apply some heat to it, you start breaking down the glue. If, for example, you have some paste, from like elementary school, you slap on this white paste, some kids eat, but you put it on a piece of paper and you heat it up, it slowly peels away. So those are weak type of forces holding matter together. Well, that's what you can do. You can apply heat to break up these forces, and you can get a liquid state. And a liquid state is when the molecules tend to tumble amongst each other. They're still attracted to each other, but now they're loosely held. So they move out of the way. So again, you apply more energy or heat, and then you can separate these chemicals from each other completely. And you have the gas phase. So we have a solid, we have the liquid, we have the gas phase. And you're just breaking down the intermolecular force between the chemicals to get through these different phases. As you remove the heat, or as the chemical releases that heat, then it goes back to its liquid state if we have a gas originally, or it goes back to its solid state if we have a liquid originally. So these forces right here, intermolecular forces, are responsible for the phases of matter. Now let me also tell you another thing about intermolecular forces, because intermolecular forces also are responsible for the different properties of matter. Some properties of matter include boiling point. Boiling point is defined as a temperature at which you need to raise a substance so that it goes from its liquid state to its gaseous state. Okay? What temperature does that occur? It's got to be, the normal boiling point would be at 1 atmosphere condition. Okay? For water, you guys know at sea level, the boiling point is 100 degrees Celsius or 212 degrees Fahrenheit. But if you were in Denver, where it's elevated, the boiling point is not 100 degrees Celsius. Is it higher or lower? Yes, no? It's actually lower. That's because there's less pressure acting on the water, so it takes less energy to get into the gas phase. So at elevated temperature, elevated conditions, the boiling point is actually lower. But nevertheless, a boiling point measures the strength of the intermolecular force. Another property that measures strength of intermolecular force is melting point. At what temperature does a solid convert over to a liquid? That's a melting point. Okay? And if matter is held together very strongly, then it'll take a lot of energy to pry them apart to get to that liquid state right here. And so the temperature is going to be higher for matter with strong intermolecular force. Another property is heat capacity. The heat capacity is how much energy will an object hold, absorb, before it undergoes a temperature change. So again, if it has very strong intermolecular force, the heat capacity is very high. There's something called heat of vaporization. The heat of vaporization is nothing more than the temperature required to get that particular object into the heat that is required to get that particular object from the liquid to the gas. It's not a boiling point. Boiling point is a temperature. This measures the energy that you need to get it from the liquid to the gas. There's also something called heat of fusion. The heat of fusion is the energy required to get a solid to the liquid. It's not the temperature, it's the energy required to do that. There's something called surface tension. How tense is the surface of that particular material in its liquid state? You know that if you have a beaker full of water, then the water tends to form a bulb at the very top. And the reason why it does that is because of its surface tension. Okay? Mercury, if you have a mercury in a tube, it also has certain surface tension. Mercury is a liquid at room temperature. Okay? It's got a certain surface tension. It basically is like an elastic membrane at the very surface that may be difficult to penetrate. The stronger the surface tension, the higher the intermolecular force. Water has a stronger surface tension, for example, than alcohol. Another property might be the capillary action. Capillary action. What exactly is capillary action? Well, you probably did this when you were a kid. If you have a beaker of water and you have like a straw, and especially, well, maybe you guys don't have a straw that's made out of glass, but if you have a glass capillary, what will happen is that the water will actually go into that particular capillary and it'll go up that particular capillary a certain height. Okay, that's called capillary action. The roots of trees have very strong capillary action. They absorb a lot of water, and they actually have such great capillary action that you can take water from the ground and bring it all the way up to the leaves 100 feet above. Okay, the capillary action is so strong. And that's because you've got water that likes to have these strong intermolecular forces, so they stick together, and as they stick together, they pull each other up. until, of course, you've got enough water above the surface that gravity starts acting on it. If gravity starts acting on it, then it's going to be going down, but the attractive force forces it up. When gravity and the attractive force are equal to each other, it stops moving up. But if the attractive force are very strong, it'll keep going up, like in the roots of trees. Okay? That's capillary reaction. Again, it measures the strength of intermolecular force. Another property that you have is viscosity. Viscosity measures the resistance of flow. You guys know that maple syrup is much more viscous than water. You put maple syrup on a plate and you tilt it over, it slowly rolls down the plate. That's because it's very viscous. It has strong intermolecular forces. It wants to stay together like a solid. Okay? Whereas if you have water there and you tip it over, it just falls through. It's got a lower viscosity than maple syrup. So these are just a few properties that you can use to gauge the strength of intermolecular force. There's one property I forgot to mention, and that's called vapor pressure. Vapor pressure. What exactly is vapor pressure? It's the pressure that a particular chemical will exert to its atmosphere. The way you measure that is, consider this example that I gave in class today. If you have a beaker, say, full of, say we have baby oil, okay? And you have another beaker full of, say, gasoline. You guys know over time that that gasoline will evaporate a lot quicker than that baby oil. But suppose we put these now in a chamber, an enclosed chamber, so that when it does evaporate, it has to be held within that particular chamber. Well, the gasoline will evaporate, and the gasoline molecules will start to fill this chamber, and it's going to get what we call saturated. There's going to be a point where most of the gasolines will evaporate, and then some of the gasoline will actually go back into solution. And so there's a steady concentration of this particular vapor in the surrounding of that particular beaker. Okay, that's called the vapor pressure. Okay, it's going to be constant because as more of it evaporates, some of it will actually find its way back into solution. And so what we have is an equilibrium. The same amount that leaves is the same amount that comes in. But there's going to be a lot of particles out here in the gas phase because it easily wants to go into the gas phase because it's got weak intermolecular force. If it's got weak intermolecular force, it doesn't want to stick together. It wants to separate. Let's take a look at oil. Oil has strong intermolecular force. And so very few is going to find its way into the surrounding chamber. And because very few finds its way in the surrounding chamber, its vapor pressure is lower. Okay? And that again is because of intermolecular force. So in these two examples, you can see that a chemical with weak intermolecular force is going to have higher vapor pressure than a chemical with strong intermolecular force. The bottom line is that all these properties right here, boiling point, melting point, heat capacity, heats of vaporization, heats of fusion, surface tension, capillary, viscosity, will be high for chemicals with strong intermolecular force. It's very difficult to separate them from each other. All of these will be high except for vapor pressure. Vapor pressure is the only one that goes down, that has the opposite trend. If it's got strong intermolecular force, the vapor pressure is low. Okay?